As we move forward into this new century, our world is growing increasingly reliant on space-based technologies. From telephones and television to global positioning systems and military reconnaissance, all of these technologies depend on our ability to operate reliably in space. With the demand for these types of services and information growing, the performance requirements placed on space-based systems are becoming extreme. At NASA's Langley Research Center, scientists and engineers are working to develop tools that will address the current and future in-mission data handling needs of space-based technologies. One example of missions with needs in this critical area is weather prediction. Our ability to predict the weather relies on profiles of atmospheric conditions provided by satellites in orbit, allowing meteorologists on Earth to observe, create forecasts, and conduct long-term climate research. The resolution of the satellite-borne instruments that make these activities possible is increasing exponentially, and as a result, is exponentially increasing the amount of data they generate. In general, current space-based instruments are designed to collect data, like the atmospheric detectors built into some weather satellites. As incoming data is gathered, it is sent to a memory storage module for buffering and/or processing. Next, the data is routed to a computing unit for processing and/or encoding in preparation for transmission. Finally, the data is sent to a downlink module for transmission to receiving dishes on Earth. This system has worked well for the relatively low data rates of past generation instruments, but newer sensors are capable of generating massive amounts of data, and that's where problems with existing technologies can begin. Adding a new, higher resolution instrument can overwhelm the avionics in two primary ways. First, the data flow from the sensor can be too fast and too massive for the memory system to absorb. Secondly, if the memory is not sufficiently large, it can't provide enough of a buffer, and the downlink and/or computing system can be overloaded. Another problem for instruments parked in both low Earth and geostationary orbits is the potential for damage caused by charged particles in the solar wind. This type of radiation can cause serious errors in unprotected electronics. The requirement to efficiently handle large data sets onboard spacecraft necessitates the development of larger, faster memories capable of operating in the harsh environment of space. In designing a larger memory for use in space, several unprotected electronic components are brought together to form a system that is protected or radiation tolerant. This was the philosophy behind the design and development of the Radiation Tolerant Intelligent Memory Stack, or RTIMS. What was needed was a system with large, fast memory, built-in error correction, a system that was both versatile and in-mission reconfigurable, and rugged enough for space applications. With these requirements in mind, electronic designs were created. These two-dimensional designs were then used to develop the electronics in 3 dimensions. And finally, the layouts were used to create the physical components of the memory module. The base of the module contains heat pipes for thermal management, and pins for electrical connection to a circuit board. As the individual electronic layers are stacked, radiation shielding is added to provide further protection for certain components. Once stacking is completed, a very pure epoxy is injected, flowing around all of the elements of the memory module and providing enhanced mechanical stability. The module is plated with a nickel and gold alloy, and a thin layer of conductive glue is then applied to secure the final layer of radiation shielding. Advanced coating techniques were used to define the module's behavior and to enhance its radiation tolerance. The completed modules are installed on circuit boards for use in advanced avionics systems. Replacing outdated memory systems with the advanced RTIMS modules will allow future space systems to easily handle vastly increasing amounts of data while enhancing reliability by distributing fault tolerance. In certain applications, RTIMS can replace both the memory and computing systems, simplifying future spacecraft designs. The Radiation Tolerant Intelligent Memory Stack, RTIMS, meeting the data volume needs of the next generation of high-resolution sensors while reducing the size, cost, risk, and development times of our nation's space-based computing systems.